Last thing in this all transport notes is just to talk about filtration. Filtration, in my mind, kind of goes with epithelial transport, but it's never usually taught until we get to the kidney. I want you guys to know about it much, much earlier. So you've probably learned about filtration before. What it is using a pressure gradient as the motivation for transport instead of a concentration or electrical gradient. So what's going to happen with filtration is that, let's see if this makes sense to you. This is the extracellular fluid, extracellular fluid, but interstitial fluid specifically. And then the fluid that's in here, right, is blood, but specifically plasma that we're talking about. Is there a pressure difference between blood plasma and interstitial fluid? Well, yeah, generally speaking, there is, because, of course, blood has a pump hooked up to it. So there is quite often, not at every point in the cardiovascular system, but there is quite often higher pressure here than there is here. High pressure here and low pressure here. And so what's going to happen in those locations is if there are any porosity or any holes at all, what happens is water and small solutes are going to get pushed from high pressure to low pressure. And so it's not at all going to be selective. It's not going to move down something's concentration gradient. It's only going to be selective by size. So little bitty things will fit through the holes. So this is actually how you get ions mostly into your interstitial fluid. So filtration is happening at every single capillary in your body because capillaries, especially at the arterial end of a capillary bed, are going to be higher pressure than the interstitial fluid. So this is not going to be selective at all, except by size. A good metaphor for this is making coffee. Now, I realize we're in Utah, but you've probably seen it done somewhere, right? So what you have is a membrane that has some pores in it. It's your coffee filter. And you've got the water that you're going to pour in. The water would go through the membrane on its own, but if you put coffee particles in there, it's going to bring the coffee particles through, but only based on size. But it's not selective because if you put dirt in there, the dirt particles would come through based on size as well, or red Kool-Aid. So it's not at all selective except by size. No ATP is required at the site of transport. You may have used ATP before to create the pressure gradient. Big things shouldn't go through. So if I put a golf ball in the coffee filter, it shouldn't go through. But if the pressure is high enough, you can get the golf ball through, but it's going to destroy the membrane. This is one of the reasons that hypertension can be really damaging to capillaries, like the capillaries in your eye and your kidneys. So examples, every capillary in the body, like I said, does filtration. And then at the kidneys, it's even better than anywhere else that to do filtration, because the pressure in the kidney capillaries is super duper high, and the kidney capillaries are really porous. So you get really, really effective filtration at the kidneys. Okay, but every capillary in the body also does it. So kidneys are going to really effectively do filtration of the bloodstream. But if your kidneys fail you, what's going to happen is you're going to have to do a process called dialysis. So let me tell you a little bit about what your kidneys should be doing and then show you what happens when dialysis is the thing that you have to depend on. Okay, so in the kidneys, and we will talk about this in much more detail later when we do the kidney chapters. What you are going to have, this is not anatomical, this is just a physiological drawing, is you are going to have two fluids that are running right next to one another. You've got blood tubes, also called capillaries, and you've got P tubes, also called uriniferous tubules, and they're microscopically separated from one another. And of course, the blood is going to be higher pressure than the urine because it has a pump hooked up to it. And so what's going to happen is as the blood tubes run by the P tubes, water should get pushed over, and it should pull small solutes like ions and things. But for right now, let's concentrate on waste products that we need to get rid of. Sorry. Like urea. And hopefully you guys remember that urea is a waste product from protein breakdown, from protein catabolism. So, and it's not problematic as long as you don't let it accumulate in the bloodstream. So these are some healthy kidneys doing what they should do, and you're getting rid of urea just by diffusion, right? So, I'm sorry, just by filtration. So this is just filtration. It's based on pressure and it's moving that direction. But what happens if your kidneys fail you? Well, if your kidneys fail you, you are going to start to accumulate urea and other waste products in your bloodstream. And you might need to do the process of hemodialysis. And with hemodialysis, what they're actually going to do is, I'm going to blow up this little dialysis thing for you in just a second. What you're going to have to do is you're going to have to cheat because filtration is failing you because you've got damaged kidneys for whatever reason. And you are going to have to do diffusion because filtration failed you. So let's look at how that would work. So this picture is going to be hemodialysis. Okay, so what we have is we're going to take the blood out, like in the picture you just saw. We're going to take the blood out of a person who's having some kidney problems, and we're going to put it through a dialysis machine. Inside the dialysis machine, there is this dialysis chamber that you're seeing there. It's not just hanging out by itself. And so what am I actually going to do in the dialysis chamber? Well, what I'm going to do is I'm going to put blood in one side and out the other to give it back to the person because it's valuable. Inside the dialysis chamber, there's going to be a membrane. It's just made of this specialized plastic looking stuff. And I'm going to run dialysis solution through it. And it's going to be running the opposite direction. So the blood's going to be going that direction. The dialysis solution is going to be going that direction. This membrane that you're seeing here is so incredibly curved that it looks almost solid. So what's going to happen? Well, the blood, because it's getting dirty, because it's dirty and your kidneys are failing you, it's going to have a high concentration of urea. The dialysis solution should have 0 urea because you don't want any, right? And then all I have to do is be really careful and make this membrane right here urea permeable. Okay. And then what's going to happen is as the blood runs this direction, okay, and the dialysis solution runs this direction, because this is urea permeable, urea is going to get pulled via diffusion, not filtration, because it's not a pressure differential. Diffusion. It's going to get pulled, and then what I'm going to do with it is dump it, right? I'm going to be running fresh dialysis solution in all of the time, okay? And if your kidneys are failing really badly, you may have to do this for hours and hours at a time. Sometimes people even have to sleep on dialysis. So it's cleansing their blood all throughout the night. So that is dialysis, which is based on diffusion. It doesn't happen in the body naturally because your filtration mechanisms at your kidney were actually failing you. And that's it for that set of notes.